everyone, and welcome to my presentation. I am Shouvik and I will present my poster presentation. The topic of my poster is on the nature of pre-monsoon coastal upwelling on the northwestern Bay of Bengal using GHRSST. I have worked on this topic under the supervision of Shouvik. Now, moving on to the introduction. So, we all know that the coastal upwelling is an important process. It is mainly driven by alongshore wind, which helps in elevating the biological productivity of the coastal region. There has been numerous studies aimed at understanding the mechanism of coastal upwelling. This study is the first study to report on the variability in coastal upwelling within a pre-monsoon coastal upwelling period. Now, moving on to the study area. The study region is situated in the east coast of India towards the north of Bay of Bengal, represented with a black box in its inside. This is the zoomed figure of the study region. The red contour represents 85 represents 80% HFRN coverage region. We have taken a line perpendicular to the coast within the region to investigate the variability. The line makes an angle of 53.6 degree with the zonal direction. Moving on to the data, we have used level 4 GHRSST data. The high resolution GHRSST data enable enable the investigation of spatiotemporal variability in coastal upwelling. Next, we have used level 4 SCAT-1 daily data. The data is available from MOSDAC. We have used high frequency radar data, which was made available by NIOT and NQuest. We have used sea level anomaly, level 3 track data, and level 4 graded daily data. The data are available from Copernicus Marine website. The salinity monthly data from SNAP, climatological salinity and temperature data from World Ocean Atlas 2018. The data used in this study covered the period from April to August 2018. Now moving on to methodology. To identify upwelling, we have used Ekman transport for identifying the upwelling signature from the wind. Now I'm not sure if these equations are clearly visible in the video, so please follow my audio and look into the PDF which will be provided to you. Now we have used the positive cross-shore component of equivalent transport as upwelling signature. For the upwelling signature from SST, we have used the difference of SST from nearshore to the offshore perpendicular to the coast, and we have used cross-shore surface current as a signature of upwelling in surface current. Now, moving on to the results, we have first identified the upwelling hotspots and the timing of its occurrence. In this figure, the first row represents monthly mean wind. The background is its magnitude. From the direction of monthly mean wind and its magnitude, it can be seen that the wind is upwelling favorable throughout the period. The second row represents mean SST. The dark blue patch in this region suggests upwelling in April and May. Also, it is clearly visible that the upwelling didn't occur after that. The third row is the monthly mean sea level anomaly plot. The strong positive SLA from June shows the presence of downwelling continuum. The last row is the monthly mean salinity plot. Here also, presence of low salinity water near the coast from July onwards represents low density water, thus more stratification. We further investigated the upwelling signature in climatology and in climatology salinity and temperature vertical section along the line AB. Here, the x-axis represents the distance from the coast and y-axis represents depth. The sharp gradient in temperature and salinity towards the coast during April and May represents upwelling. Now, once we have identified the hotspots in upwelling and the timing of upwelling from previous to analysis, we investigated the various upwelling signatures along line AB, which is shown in this figure. Here, the x-axis is time from 16th April till first week of June, and the y-axis is distance from the coast. The top panel represents Ekman axis. In the figure, all the active and break phases are not clearly visible. The dark brown patches represent upwelling phases. The second row is Ekman pumping. Here, all the upwelling signatures are not clearly distinguishable. The third row is the SST-based upwelling index. In this figure, the three active upwelling phases and each followed by break phases is easily visible. The active and break phases are differentiated based on increase and decrease in the horizontal extent of upwelling index. The fourth panel is the cross-shore surface current. Here, all the three active and break phases are clearly visible, and is perfectly it it perfectly syncs with the SST variation. As you can see, whenever the horizontal extent is increasing, uh, there is a strong signature of upwelling in the current, and during break phases, the cross-shore current is absent, which is represented with the negative values. Next, we investigated the spatial pattern of surface current, wind, and SST. Here, here column 1 and 2 represents mean plot during active phases and 3 and plot during break phases. Column 1 and 3 for wind and 2 and 4 for surface current. The 3 row represents 3 phases. In this analysis, we have found that during active upwelling phases, a strong cross-shore surface current is formed. As you can see uh, in this three figures during three active phases, and which is absent during break phases. As you can see during break phase, in this fourth column during break phase, those strong cross-shore currents are absent. And the wind is also alongshore during active phases and is not perfectly aligned with the coast during the break phases. We further investigated the variability of upwelling in sea level anomaly track data sets. Now, since the daily track data is not available at a particular location, we collected SLA data from available satellite sensors such as Cryosat-2, JSON-3, Sentinel-3A, HY-2A, Solar Altica within the upwelling region. The data collected points are shown in this figure. The SLA variability within the upwelling region from April to May end is shown in this top panel, and from June to August is shown in this bottom panel. The SLA track data also captures the upwelling variability. It is found that during active phases, the SLA dropped slightly, while during break phases, it rose sharply. The SLA was positive from June onwards, suggesting the presence of downwelling Kelvin wave. Now, moving on to the conclusion. Through this study, we found that the GHRSST and current index are better than Ekman transport-based index in identifying upwelling. We have identified the presence of active and break phases during an upwelling episode. The current responded immediately to upwelling. SST had a delay of 2 to 4 days. The upwelling extended from 75 km to 140 km during peak active phases and receded up to 45 km during peak break phase. Temperature dropped by about 3.5 degrees centigrade during peak active phase. The cross-shore current also extended from 45 to 135 km and speed up to 1 meter per second during peak active phases and were absent during break phase. Thank you.